So the first thing we need to make clear when we're talking about causality and causal inference is we need to make a distinction between association and causation, or associational inference and causal inference. And that's what I'm going to do in this part of the lecture. So the models that we've covered in the course so far take this general form here, conditional expectation, and we use our regression function to model that conditional expectation where y is the response variable and x is some covariates. And we've looked at different types of models. We started with a linear model, we looked at linear mixed models, we've looked at generalized linear models, semi-parametric models, GAMs, generalized additive models, and so on. And our ultimate aim in formulating these models is to infer aspects of what we call the data generating process. That is the process that generated the observed data. Now the DGP, the data generating process, that comprises all the relationships between the variables in our model. So that comprises all of the relationships between y and covariates x, and between the covariates themselves. But in terms of the data that we have available for our models, we can categorize data according to the DGP in one of two ways. First, we might have experimental data. These are data that are generated through a controlled experiment conducted on defined units that we're studying. And what that means is, because we have experimental conditions, then the research design can actively control the conditions under which the data are generated, and therefore the DGP is largely known. We can manipulate the data generating process in an experiment to test or emphasize certain features of interest. So for instance, we could test whether a treatment that we're interested in has an effect by randomly allocating it to some units in the sample, but not to others. That would be one example of an experiment. That contrasts with observational data. Observational data are generated via sampling, so through survey or through observation, through measurement, from a population of units. And in this case, the research design involves just passive observation to collect the data. And in that context, the data generating process is unknown. So someone gives us data from a survey, or we measure data in the real world, and we simply take the data as given. We don't actually intervene in its production. We don't change things so that the data are generated in different ways. We just observe the data and we then go and analyze it. And that means that the data generating process, the structure that gave rise to what we observe, is unobserved. It's not known to us. Now that's the data that often statisticians, more often than not, statisticians are dealing with, observational data, and that's going to be our focus in this lecture. We're going to focus on observational data, which describe outcomes and characteristics of units for an unknown data generating process. And we're assuming, therefore, that we don't have access to experimentation. Now, our aim is to infer aspects of the causal structure of the unknown data generating process. That is the aim of causal inference, stated here under definition 3. So causal inference aims to identify and measure causal relationships from observational data using assumptions about the data generating process to disentangle causality from association. And these are really two important words, obviously, given the title of this section, that we're going to look at and that are key to what we're talking about in this lecture. So to explain what they mean, let's assume we've got two random variables, x and y, with joint density given by this density here, and x and y are not independent. Remember, this symbol here, this symbol that's been crossed out, means independent, and we cross it out, that means not independent. The fact that these relationships, the fact that x and y are dependent, can be stated in terms of one of two things. First of all, we can state it in terms of association. Association simply says that there is an absence of independence between the two variables. It implies that x and y are related in some way, in the sense that observing y, is helpful in predicting or informative in some way for what we know, observing X helps predict or is informative in some way for what we know about Y. And so, for instance, we could conduct a correlation analysis, we could conduct a regression, we could look at a scatter plot, and that will show us association between two variables, X and Y. Causation, on the other hand, implies something much stronger. Causation implies that X has a direct influence on or causes Y. That is, there's a direct cause-effect relationship in the sense that if I change X, that will cause a change in Y. And therefore, under causation, what we're saying is we can make the event that Y takes some particular value more likely by changing X, by manipulating it. So let's look in a bit more detail at what this really means, and it'll become more apparent as we go through the lecture. So we know from lecture 1 that two variables, random variables, are independent. If they're independent, then their joint density factorizes into the product of two marginals. Importantly, if variables are independent, you see here, this is just a chain rule for random variables, we're saying that conditioning random variable X on Y makes no difference. It's just the same as the marginal distribution. Conditional, the same as the marginal here, because X is independent of Y. So conditioning on Y makes no difference. It doesn't provide any additional information about the distribution of X. Independence is absent, that is, X and Y are dependent or associated if the conditional distribution is different from the marginal. And again, we covered that in lecture 1. But the fact that the conditional distribution is different than the marginal, the fact that these are not the same, the fact that they're associated, does not mean that they're causally related. It doesn't mean that X causes Y or that Y causes X. And I'll give an example in a second. So association then is a necessary but not sufficient condition for causation. But conversely, causation implies association as a necessary condition. So association is a necessary condition for causation. Causation implies association, but not the other way around. So association is, in a sense, just a descriptive finding. We know that X and Y depend on each other in some way if they're associated, and we can model and observe that association quantitatively. So for instance, in a correlation coefficient, in covariance, in a parameter from a regression, or via a graphical plot such as a scatter plot. But causation is saying something stronger, something more analytical. It's saying that by changing X we will cause a change in Y, this bit here. It's a stronger claim than association, and for that reason it's more difficult to establish empirically. We have to put more conditions on the problem if we're going to make a causal interpretation. And so this leads to a well-known phrase that we use in statistics, which says association does not imply causation. They're not the same thing. And I'll give you an example of this. There is an association between ice cream consumption and drowning. It's a positive association. So as ice cream consumption goes up, we observe more people drowning. Now, why is that the case? Well, the reason why that's the case is that as the temperature grows, good weather, people tend to consume more ice cream. They also tend to go to places and swim. And that's why the two are correlated. We don't really believe that as an individual eating ice cream is going to increase my probability of drowning. And we don't really believe that if I'm drowning, I'm more likely to eat ice cream. That's a nonsense. The only reason that association exists is because of a common factor, that is weather or temperature. That's what's driving the association. So that's an example of an association that's definitely non-causal. Okay, so in this lecture we're going to use two different routes to represent causality. We're going to do it via graphically, via what's called directed acyclic graphs, and we're going to do it mathematically. And I just want to introduce this now because it's going to be important in our analysis. So causality can be represented graphically using what's called a directed acyclic graph, or a DAG. And a DAG represents a probability model very, very simply using just a combination of nodes or vertices and edges. So in a DAG, each random variable is represented by a node, and each edge connects a pair of nodes together. The DAG is directed because the edges imply a direction. That is, they're arrows. So an arrow connecting two nodes indicates that the first variable causes the second. And a DAG is acyclic because there's no cycles within the diagram. A variable cannot cause itself either directly or through some other variable. So for instance, here's a DAG shown below showing causal relationships between a response variable y and three covariates x, d and u. And this DAG shown here is actually a very, very typical DAG that we study or that we use. It's basically a structure that's very, very common in causal inference. So in this case here, let's start with y, the response. The arrows into y indicate that this response is caused by x, d and by u, but not the other way around. Similarly, d is caused by x, but not vice versa, and y is caused by u, but not vice versa. So that's an example of a directed acyclic graph. It's really that simple. Nodes are random variables, they're connected by edges, and the direction of the edge gives us the causality that's assumed in the model. Now we're also going to write causal structures mathematically using, I guess, probability random variable notation. So for instance, the causal graph above, the causal DAG above, could represent the following probability model or data generating process. Sorry, I just noticed an error there that I've just corrected in real time. Okay, so this is the probability model written in probabilistic notation. We have y normally distributed with a mean that depends on d, x and u, and a variance given by sigma square y. D depends on x. It is Bernoulli distributed with parameter p determined by x, the probability. X is normally distributed, mean mu x, sigma squared x, and u is normally distributed, mean mu u, sigma squared u. So that is this DAG written in mathematical probabilistic notation, and we're going to use both in the lecture. Note that in the mathematical form we've been able to specify additional details. So this just tells us the causal structure, but now we've written out also the distributions and the moments of a distribution, normal and Bernoulli in this case, but it could be any form, of course. So although the directed acyclic graph and the mathematical representation of the DGP above are intended to show causality, they actually also reveal how non-causal associations can arise. And so we can imagine, and we're going to give examples of this later, let's say D is ice cream consumption and Y is drowning. It's this variable weather up here that causes the association between the two. Let's say there's no arrow here, an association is caused by a kind of spurious association, if you like. So we can demonstrate causality, but we can also demonstrate non-causal associations and lack of associations within a DAG. So for instance, here we can see that U is not associated with X. Deficiencies in representing causal structures fully and accurately via observational data is what makes causal identification challenging. So typically we don't know this data generating process, and we've got to represent it in some way and represent the causality that's embedded within it. And that is the challenge that we face, and we're going to talk about why that challenge emerges in the next part of the lecture.